All right, guys, good to see you again. In the previous class, actually, I saw 19 students, but in attendance list, 3 students submitted only blank. What is it? That's paper. Okay, that attendance sheets. I don't know why you did so. If you did not actually write your name and surname, I'm not going to take as present. Okay. Guys, let's continue. And that's our last class. So you have to prepare until for 6.4 for your final exam. Chapter 5, Chapter 6, 1, 2, 3, 4, plus optimization problems or applied optimizations from Chapter 4. Okay. So you will have around 12 questions in your final exam. So now we are going to use those ideas, the ideas in 6.1 and 6.2 and 6.3. And now we're going to add one more thing, one more tool. Now we're going to deal with the surface area of a solid, which is obtained by revolving kind of region about the x-axis or y-axis or about some kind of, what is it, horizontal line or a vertical line. So when you jump rope, the rope sweeps out the surface in the space around you, similar to what is called a surface of revolution. The surface surrounds a volume of revolution, and many applications require that we know the area of the surface rather than the volume it encloses. In this section, we define areas of surfaces of revolution. More general surfaces are treated in chapter 16. Very simple example is now you'll see a lot of, what is it, containers or bowls or some kind of, what is it, big water reservoirs, right? So actually, sometimes, most of the time, we need to paint them, right? Before we use this, like Coca-Cola can, for example, right? Or fish cans, you need to, what is it, paint it. Now, if you're going to paint maybe a few things, it may not be important for you because you just go to the market and buy, just use a little bit, okay, and the waste, you just throw it to the trash, okay? But how about if you're talking about millions of such things, right? And let's say you are running a factory and every month you are manufacturing, let's say, 1 million pieces of such bowls and you have to paint. So actually it requires some calculation how much paint is needed to paint all of this, what is it, containers. So at that time you need to do some calculation, right? For 1 can, how much paint is used, and after multiply by the number of cans, that's your production level in a month, right? And accordingly, you can actually give your order. So before I continue this, you have to know two important things, okay? Because what we are going to obtain, the formula that we are going to obtain is based on this basic area formulas. Now, in the first picture, you see, what is it? It is a cone. Okay. You see a cone, right? So not including its base. Let's say just only its curved surface area, the curved surface area, not including its base. And what is its area? Its area is equal to, curved surface area is equal to pi, and base radius, it is r, and slant height, the slant height, let me just label this by L or S, it doesn't matter. Let's say it is L. Okay, and we don't have much time here. That's why I'm not going to prove it here. I proved this in the class, but now online class, it may be a bit boring for you. That's actually how we find the curved surface area of the cone. Now, if I just chop off the top of the cone, okay, with a kind of plane, okay, or knife that is parallel to the base, okay, chop off, and we will get something. So the something is called frustum. That is frustum of a cone. That is, we call this frustum. Okay, then the question is, what is the curved surface area? Not the top, not the base, or the curved surface area of this frustum. So the curved surface area of this frustum is equal to pi times, and here we have slant height. Slant height is this. Okay, again, this one is slant height. Okay, that is L times, and here we have, what is it? R plus R. So this capital R is the radius of the base. So this one is capital R, and the top is lowercase r. Okay. Now also I can just rewrite it like this. I can write it as 2 pi times and R plus R, capital R plus R over 2 times and here L. Okay. Now you will see that what is L? L is this curve. So, what is the slant height, right? So this 2 pi, this actually this the average of the radii of the top and the bottom bases, right? And multiplied by L. And actually, exactly, we are going to use the surface area of revolution. When you change this, you will see that actually this surface area, if you're given some kind of curve, actually, if you revolve this above the x-axis, you will have kind of another curve right here. So we will have this kind of container. We will have this kind of container. We will have this kind of container. And how do you find actually the surface area of this container? You will see that the surface area of this container will be integral. So if this point is A and this point is B, right? That is the graph of the function. Let's say y is equal to f of x. You will see that's equal to A from A to B. Now here we have 2 pi. Here we have 2 pi and r plus r over 2, this average, right, using mean value theorem, that's equal to f of x. And the length is this length height, right? What is this length? And we have just talked about the arc length, that's equal to 1 plus f prime of x. And here we have squared, and that is dx. Let's see here, this one is our 2 pi. Just right here. That is our 2 pi, and that's 2 pi. And that is the average height. That is the average height, right? That is the average height. This one is a height, average height. And how about this L? This is the average height. L is, this part is, that's our L. Okay, so that's it. So now let's start. If you revolve a region, suppose we are given a region, right, in the plane that is bounded by the graph of a function over an interval AB. It sweeps out a solid of revolution because that solid is obtained by revolving some kind of region. That's why we call this a solid of revolution. However, if you revolve only the bounding curve itself, okay, not the region, not only the curve, so it does not sweep out an interior volume, but rather a surface that surrounds the solid and forms part of its boundary. So we are just talking about the container, right? Inside it's empty, only it has the boundary. So just as we were interested in defining and finding the length of a curve in the last section, we are now interested in defining and finding the area of a surface generated by revolving a curve about an axis. So again, suppose that we are given a kind of function, okay, for this Frustum, we have already obtained a formula, okay. So now if you revolve this kind of function, kind of curve over the interval from A to B, right, this blue one is the graph of the function over the closed interval AB. Now if you revolve this, we will have this kind of, what is it, container. Now, again, I am going to choose n points, or I'm going to divide this AB into n sub-intervals. Now, just considering one of them, it will have some kind of band here, right? Let's see here, this PQ, we're talking about this BQ. So then what is the area of this one? If you just unfold this, right? So the area will be approximately equal to 2 pi f of xk minus 1 plus f of xk over 2. What is this? That is R2 plus R1 over 2, right? And the length of the curve. So the length of the curve is approximately equal to delta xk squared plus delta yk squared. That's the approximation. The Frustum surface area is approximately equal to this. So now if you just make some adjustment, I will get this formula. Again, what's actually here is if our k goes to infinity, right, infinity, you will see that I'm just for the length, I'm going to use this formula, and we will get, what is it? That's I have just shown you at the first slide. We will get this 2 pi, and y is the height, the average height, and 1 plus dy dx squared. Dx, exactly what is it? It's the length, the arc length formula, right? That's the arc length. And this one is the height, and this one is a 2 pi. Okay, so that's it. That's how we find the area of the surface of revolution. Now let's focus on using this formula, how we're going to use this to find or to solve the questions. Okay, find the area of the surface generated by revolving the curve y equals 2 times x squared of x, where x changes from 1 to 2 above the x-axis. Now, actually, you see here is a little bit more complicated than the arc length. Not complicated, it's involving more expressions, right? So to do this one, our function is given, is changing from 1 to 2, it's fine. The first thing I have to obtain here is I need to calculate this thing. What is 1 plus f prime of x squared? Okay, So that's equal to 1 plus, what is f prime of x? That's equal to 2 times 1 over 2 times x to the power of 1 over 2 minus 1 over 2. That's equal to 1 minus 1 over 2. That's equal to minus 1 over 2. And here we have squared. Now, if you simplify this, that's equal to 1 plus, what is it? X to the power of minus 1, right? X to the power of minus 1, that is 1 over x. Okay, or maybe I can just write it as x plus 1 over x. Okay, the second thing is I'm going to write our form. So the surface area is equal to integral. Our x is changing from 1 to 2. And here we have 2 pi times our function. What is our function? That is 2 times square root of x. Times, now here we have square root of 1 plus f prime of x squared. That's equal to x plus 1 over x. That's it. Here we have the x. So that thing gives us the surface area of this, some kind of, what is it? Not container, actually. I'll call this. I think it looks like a kind of ear, right? So that's equal to, now 2 pi times 2 is 4 pi. There's 4 pi. And integral from 1 to 2. The square root of x, they cancel each other. So here we have square root of x plus 1. So this dx, right, that is equivalent to the differential of x plus 1. X is changing from 0 to 1. We don't want to 1 to 2, or 1 to 2, right? It's 1 to 2. So that's equal to 4 pi. So now x plus 1, x plus 1. So here we have x plus 1 to the power of 1 over 2 plus 1. That is 3 over 2. In front, here we have 2 over 3. And integration limits from 1 to 2, which is equal to 4 pi times 2 is 8. 8 pi over 3. And when it is 2, 2 plus 1 is 3, right? So here we have 3 to the power of 3 over 2. Minus, when it is 1, it is 2. It is 2 to the power of 3 over 2. Okay, or I can just write it as, what is it? 8 pi over 3. And 3 square root of 3 minus 2 square root of 2. Okay, you can just leave your answer like this, unless it is stated differently. Like, for example, maybe after getting the final answer, leave your answer corrected 2 decimal places. At the time, you can evaluate and leave your answer corrected 2 decimal places. Okay. All right. Now, another thing is, how about surface area for revolution about the y-axis? How about if you revolve that curve, right, that piece of curve or arc, not about the x-axis, about the y-axis? At the time, we will have something that is vertical, right? This first one is horizontal. Now we'll have something vertical that's standing like on the ground. So if x equals g of y is non-negative, is continuously differentiable on CD, the area of the surface generated by revolving the graph. Now, why we are saying continuously differentiable on CD? Because here we have dx dy, right? And here we have derivative in our function here in the integral. And that's why it must exist. Otherwise, if it is not continuously differentiable, at some point, actually dx dy, it does not exist, then it doesn't make sense to talk about this. We have to add some more conditions here. So the area of the surface generated by revolving the graph of x equals g of y about the y-axis is, everything. Again, we are just interchanging the roles of x and the y. Let's see one example. The line segment x equals 1 minus y, where y changes from 0 to 1, is revolved about the y-axis to generate a cone. One is lateral surface area. Okay, so lateral surface area, which excludes the base area. So here is asking, find is lateral surface area, which excludes the base area. If you say just surface area, usually we include also this base area. So now if you just see that lateral surface area, that means that we don't need a base because maybe it's standing on the ground and we don't have to use any material to cover its base. That's why just we need only the lateral surface area. So again, our equation is x plus y is equal to 1, right? And we are just revolving this about the, what is it, y-axis. Again, if you just interchange this, instead of x, I can write y instead of y. I can write x. It will have. I can use exactly the original formula, but here is fine. So let me just express x in terms of y. That's equal to 1 minus y, right? Let's see here, our y is changing from 0 to 1. So y is changing from 0 to 1. So the second thing is we have to evaluate the thing. 1 plus dx and dy squared, right? That's equal to 1 plus, what if you differentiate x with respect to y? That's equal to negative 1. Negative 1 squared, that's equal to just 2. Then number 3, we can find the surface area. And the integral, y is changing from 0 to 1. And here we have 2 pi times our function. What is our function? 1 minus y. Times is high. Times the length of the curve. That's equal to square root of is equal to 2. And here we have dx. That's it. Now this 2 pi and square root of 2, they are all constant numbers. We can just keep this outside this integral, right? So that's equal to 2 square root of 2 pi. And here we have 1 minus y. So that is y minus 1 over 2 y squared from 0 to 1. So which is equal to 2 square root of 2 pi. When it is 1, it is 1 minus half, that is 1 over 2, minus 1 it is 0, that's equal to 2. So the surface area, lateral surface area of this cone is equal to, what is it? 2 to cancel each other, square root of 2 and pi. And also usual way, if you evaluate, how do you find the surface area? If you remember, the surface area is equal to pi r L, right? In the beginning of the chapter, actually, we mentioned this pi times, what is this radius? Radius is equal to 1. And if it is 1 and 1, right, using Pythagorean theorem, so that is 1 and 1, hypotenuse should be equal to square root of 2. So this line height is equal to square root of 2. That's equal to square root of 2 pi. So both actually things, they agree with each other. All right. Guys, we have 2 more examples. Okay, that's it. Let's see here, we don't have much thing. The only thing you have to do is you need to practice. And if you just practice 3 or 4 questions, I think it will be crystal clear for you. Because without learning or practicing questions, we cannot learn math. We cannot understand, or we cannot have or obtain gain any intuition. Find the area of the surface generated by revolving the curve x equals 2 times square root of 4 minus y about the y-axis over this interval. Again, a similar question. We have just done this. It's a little bit different. So our function is this, right? Everything will be with respect to y. Number 1, we have to evaluate this. 1 plus, let's say, the g prime of y. I have to for new function, right? And square this. So 1 plus, what is the derivative of x with respect to y? So that's equal to, here we have 2 times, derivative is 1 over 2 times differentiate this, it is negative 1 times 4 minus y to the power of minus 1 over 2, right? And here we have squared. So that is equal to 1, 2 to cancel each other, negative 1 squared is plus. So that's equal to plus 1 over square root of 4 minus y, right? Okay, the second one is, the second step is not direct. I can write the surface area. So we have 2 pi, I can just keep 2 pi here, is a constant number, integral, and our y is changing from 0 to 15 over 4, 15 over 4. So 2 pi, our function is 2 square root of 4 minus y, right, times, and what is this square root of, is this right? It is, I think it is 2, negative 1, something is set like this, right? Because minus 1 over 2 times 2 is negative 1. 4 minus y to the power of minus 1 is 1 over 4 minus 1. Right? So that's equal to, I can simplify this further, 4 minus y plus 1, that is 5 minus y over 4 minus y. So that's equal to then square root of 5 minus y over 4 minus y. And here we have dy. That's a good thing. Actually, there's 4 minus y, 4 minus y. They can each other because under the square root, right? So what do we have here? Here we have also 2 is constant, 4 pi integral from 0 to 15 over 4, and the square root of 5 minus y. And dy, also I can dy, right, as, what is it? 5 minus y. So here we have negative 1, because differential of 5 minus 1 is minus 1 times dy. Now, I can just integrate this with respect to 5 minus 1. So here we have 5 minus y to the power of 1 over 2 plus 1, that is 3 over 2. So here we have 2 over 3, just change it from 0 to 15 over 4, which is equal to, so here we have minus 8 pi over 3, right? So when it's 15 over 4, so here we have 5 minus 15 over 4 to the power of 3 over 2 minus, when it is 3, 0, that is just 5 to the power of 3 over 2. Maybe we can simplify a little bit further. So here we have minus 8 pi over 3 times, and 4 times 5, 20. 20 minus 15 is 5, right? And 5, so 5 to the power of 3 over 2. Okay, it's a common factor. And 4, square root of 4 is 2, to square cube is 8, 1 over 8. 1 over 8 minus 1, so minus 7 over 8. So that's minus 7 over 8 times 5 to the power of 3 over 2. That is 5 times square root of 5, which is equal to this 5, 5, 8, 8, they cancel each other. Minus minus is plus. So that's equal to 35 square root of 5 over 3 and the pi. So that is the surface area of, I think, let's call it a revolution. Okay, that's the last example. You are so quiet. I hope everything is clear. And if you have questions, I'm here. Your final exam is, I requested them to schedule this on the last day, Friday, so that you have more time to practice. Okay, you have Tuesday and Wednesday and Thursday. If you have any questions, I'll be in my office. If you just let me know a bit earlier, or actually arrange an appointment and come, it is fine, okay? So even if you actually 4 or 5 students together, if you want to come, I can arrange additional problem solving session class if you need any help. The last question, find the area of the surface generated by revolving the curve y equals 1 over 2 x squared plus 1. So here's just our quadratic function, right? And over the interval from 0 to 1, so it may be something like this. So that is x-axis, and this one is y-axis. When x equals 0, it is 1 over 2. When x equals 1, it is 1, right? When x equals 1, let's say it is 1, so it is 1, so it is somewhere here. So it's parabola, it must be something like this. Okay, parabola. All right, so parabola. Now we are revolving this about the x-axis, right? So about the x-axis means that here we have again 1 over 2, 1 over 2. So it will be something like this. Okay, this curve is something like this. Okay. Now if you revolve this about the x-axis, you will get kind of container. Okay. Okay, something like this. Okay. Can just anyway, it's a kind of container. Okay. So what are we gonna do here is, in the first step, again, we need to evaluate, what is it? 1 plus f prime of x squared. That's equal to 1 plus, if you differentiate this, here we have 1 over 2 times its derivative is 2x, right? Its derivative is 2x. As simple, it's just equal to x. That's equal to x squared. Okay. And the second thing is the surface area would be equal to, let me just write 2 pi here, integral x is changing from 0 to 1, and our function here, our function is 1 over 2 times x squared plus 1 times square root of, what is it? That thing, that's equal to 1 plus x squared. So here we have dx, right? So 2 pi times 1 over 2, that's equal to 1. So here we have pi and 0 to 1. X squared plus 1, square root of x squared plus 1, that's equal to x squared plus 1 to the power of, what is it, 3 over 2. And here we have dx. But how do we differentiate this? I mean, integrate this? Using simple methods. Interesting. We need to use signed trigonometric function substitution method, but we didn't learn that method yet. So let me check one more time. Our function is 2 pi times f of x, that is x squared plus 1, and the square root of 1 plus f prime of x. So f prime is equal to just x, and the square root is x squared, 1 plus x squared dx. So that is 3 over 2. Interesting. Just a second. Let me check the question. Did I copy this correctly or 21? X squared plus 1 over 2. X squared plus 1 over 2. 1 over 2. Thing is wrong. Okay. Without using trigonometry, square root of x squared plus 1 to the power of 3 over 2 dx. Find the area of the surface by revolving the curve about the x-axis over 0 to 1. Okay, here we have 2 pi times f of x. That's x squared plus 1 over 2 times 1 square root of 1 plus f prime of x squared. So 1 plus f prime of x, that is x squared, 1 plus x. So x squared plus 1 to the power of 3 over 2 dx. Okay. Guys, I will say this problem because using simple method we didn't learn, I don't think we can solve this. By introducing new substitution, we can do that, but we didn't learn this method yet. I have to change this x squared. We have to actually introduce this tangent of theta that's equal to x, then tangent square root of theta plus 1 that's equal to secant square root of theta. And they cancel each other. We have secant, but we didn't learn this method. Anyway, let me have a look. Okay, I will share with you the solution. Guys, let me finish the class. I don't want to take your time. The last question is interesting. Maybe I'll check the question one more time. Okay. So I will share you another link. We have 13 people now.